Our speaker tonight is Kevin Birdwell. Kevin is a research scientist at the Oakridge National Laboratory in Tennessee. He has a PhD in physical geography with an emphasis in paleoclimate and environmental change from the University of Tennessee, Knoxville. He has 35 years of experience in meteorological operations and research and nuclear energy safety. He serves as a Reasons to Believe scholar and volunteer apologist. So please join me in welcoming Kevin Birdwell.
So just as I begin, so I'm going to start off talking about sort of the basics of nuclear energy, just to kind of provide the framework, and then I will shift over a little bit into the climate topic and relate that to energy, and then we will end up back uh, finally with some of the advanced reactors and thorium energy and that kind of thing. And realize also that this is a very abbreviated version of these topics. I have much more extensive slides on all of these. So this is going to be just a bit of an abbreviation tonight. But okay, so one of the things that we need to realize about energy is there are some basic requirements that we need to think about. Um, Not just any energy source will provide what we need for our society uh, in the same way. We have to think about at least six principles, and these are resilience, scalability, abundance, affordability, reliability, and flexibility. So, resilience would be uh, under what environmental circumstances can your energy source operate? Scalability would be related to things like, well, is it useful at a local scale or a large scale or in between? How abundant is it? Because that affects how affordable it is and how useful it is. Um, that obviously bleeds into affordability, how economical it is. Is it reliable? I mean, is it there all the time or is it there some of the time? Um, for example, that can be a problem with wind and solar. Um, is it flexible? Can you transport it somewhere? Like an oil tanker, for example, you can move it from, Wyoming to Oregon or something. Um, all of those things matter in the usefulness of your energy source. And when we look at nuclear power, particularly, um, commercial nuclear power started in the 1950s and ramped up dramatically into the in the late 60s and especially in the 70s and 80s. So that's when most nuclear power plants were constructed. You can see that there's a very large fall off there in the late 80s and not nearly as much construction in the 90s. It almost came to a halt in the 2000s and then has picked up again uh, in the 2010s and 2020s, and but not to the extent that we had some 50 years ago. And what you see there below that zero line are basically plants that were retired. Um, but it is ramping up again with generation 3 and 4 reactors. And I think we'll probably see much more increase in the coming years. You can see there denoted on the chart the three major accidents that most people know about, 3 Mile Island, Chernobyl, and Fukushima. Um, and I think that brings up the topic of nuclear safety, which I will just briefly touch on here. I actually have an entire talk that I gave to RTB um, about a year ago on nuclear safety, particularly focused on the Chernobyl accident and to some degree the Fukushima accident. And unfortunately, those accidents really tainted the nuclear industry especially Chernobyl. And the unfortunate thing about that is, even though we had those accidents, overall nuclear power in terms of a per terawatt hour basis is among the safest forms of power production that we have today, even with those accidents included. And I won't say too much about it, but I think it's worth mentioning that Chernobyl, which is by far the worst nuclear power plant accident, period, was at least an order of magnitude worse than Fukushima, and Fukushima was an order of magnitude worse than Three Mile Island. In fact, um, if you take a plane ride from, say, California to Tennessee, you're going to get more radiation in that plane just because you're closer to space than you would have gotten living in the town where Three Mile Island happened. The amount of radiation that was released was very small. The only one of these accidents, and in Fukushima, while it was serious, I'm not aware of anyone that actually died in Fukushima. It was really more of an economic disaster. Um, and that was primarily a result of uh, corners cut in construction, you might say. There's another nuclear power plant in Japan that's even closer to the epicenter of the earthquake that caused that tsunami that you never heard of because they didn't build it so close to sea level, even though it's on the coast. And so it wasn't damaged at all. When they built Fukushima, they decided to cut down uh, the land facing the ocean, and so that it was easier to bring in construction equipment. And that's one of the reasons that the backup generators were vulnerable to the tsunami. Uh, Chernobyl was just simply a case of very poor design, I think is the primary reason. I don't think you can blame the people running the plant entirely for the accident because uh, they just cut a lot of safety corners with Chernobyl. That's what's called an RB. Uh, oh, I'm forget. It's a type of reactor that's no longer made in Russia, but there are actually still RBMK, I believe is the designation. But it's no, there's still about six of them in operation. They've had some safety upgrades, but the bottom line is that reactor would have never been built in the West. So the fact it's very unfortunate that it had that kind of an impact on nuclear power's popularity after that accident, since there's just no way it would have ever happened in a Western reactor. And I'd love to go into that, but I don't want to be here all night. But you can see here that basically solar, nuclear, and wind are by far the safest forms of energy in terms of accidents per terawatt hour. Now, when we talk about nuclear power, what we're really talking about is splitting atoms to generate heat. And they're and so really what we're doing is we're bombarding uh, certain types of atoms, namely uranium 235, plutonium 239, or uranium 233, um, with neutrons to cause them to split. And if you do it correctly, then the uranium atom, for example, splits and produces two spare neutrons, at least two, that then allow the process to continue by hitting additional uranium atoms, and it continues the process in a chain reaction. Um, there are really only three elements that you can do this with. Or three atoms. That's uranium 235, uranium 233, and plutonium 239. Um, Uranium 235 is really what's used in 99% of nuclear power production today or more. Um, Plutonium 239, because of its use in weapons, is not generally used, although it may be produced in small quantities as a result of uh, nuclear power plant reactions. And U-233 is something I'm going to talk about more because that's tied into using thorium. But basically, this is how you achieve criticality. You keep the process going, but you need to have at least a couple of spare neutrons around to hit additional uranium atoms to keep the chain reaction operational. And of course, that produces heat, and that heat is then transferred through heat exchangers, typically to steam generators, which then turn turbines and produce electricity. So really, once you get outside the reactor itself, the way that a nuclear power plant operates is very much the same as any other power plant, a coal plant or a gas plant. So this is just describing the difference between fertile and fissile materials. So I said there were three elements or three atoms rather that you can use for nuclear power, but there are also a few other ones that you can convert into those atoms by basically throwing neutrons at them. And those primarily are thorium-232, which is what we'll end up talking about, and uranium-238. Now, uranium-238, that works better with something called a fast neutron process, which I will only briefly describe here in a moment. But basically, U-238 is much more difficult in most reactors that we have today to use as a fuel source. Some of it does get burned up and does get converted, but it's a very small amount compared to U-235. So we generally want to use U-235 in nuclear power plants. But you can also convert thorium, and it's a process that takes about 4 weeks with all the radioactive decays, primarily there in the last decay there where you see the 27 days. But you end up with uranium-233, which is fissile and can be burned in a nuclear reactor. Now there are a lot of reactor designs, and but primarily I would say maybe 60% of the reactors in the world today are what are called pressurized water reactors, or PWRs. We have in the nuclear industry, we have abbreviations for all these reactors, and basically it's similar to what I just described. So you're essentially using water as a coolant and to some degree as a moderator as well, and I'll explain what that is in a moment. But um, you're you're essentially transferring heat from the nuclear reactions to the water, which then gets transported to a steam generator, and then that goes to a turbine to produce electricity. Um, in a boiling water reactor, the only difference is that the water in the reactor is allowed to boil, and so it directly produces steam that goes into uh, the turbine. So you kind of eliminate the steam generator process. Um, the RBMK reactors that used to be built in Russia, which is what Chernobyl was, um, once, of course, those went out of vogue after the accident, the Russians came up with what's called the VVER reactor, water-water energetic reactor. It's very similar to the PWR reactor. About the only main difference I can see is that the steam generators are sideways in the plant instead of vertical. And I'm not sure why they decided to go with that. I've heard Russians say that that's a superior design, but I haven't really found much evidence to say it is or it isn't. Um, and then there's the CANDU reactor, the Canadian deuterium uranium reactor. These are used primarily in Canada and also in India to a large extent. And what's interesting about CANDUs is um, unlike most other reactors, you have to enrich, 99.3% of the uranium you dig out of the ground is uranium-238. And as I said, that's not as useful for nuclear power. You're really after the uranium-235, which is only 0.7% of the natural uranium. So generally what is done is this is enriched uh, it's enriched, it's basically converted to uranium hexafluoride. It's as a gas, it's spun around, and the U-235 is separated from the 238 to some extent, and it's enriched to about 3 to 5% uranium-235. Well, that is more what the typical reactor needs in its fuel rods, and so that's what's typically done. But because the Canadians back in the day did not really have access to a means to enrich the uranium that easily, they came up with a way to use natural uranium that's not been enriched, just the raw 0.7% uranium. So that's what the CANDU reactor does. And the way that it uh, gets around the problem of not having enriched uranium is it uses heavy water instead of regular water as its moderator, and that the heavy water is a little bit, the deuterium is a little bit more effective at reflecting the neutrons back into the reactor so that the process of reaction can continue. And then what we're going to end up talking about by the end are molten salt reactors. These were invented in the 1950s and 60s, actually at my workplace. Um, and we had one that was functioning in the 1960s, maybe up till about 1970. Um, and I'll talk more about that in a minute, but that's a very different process because with a molten salt reactor, you have um, the fuel dissolved in a liquid medium. Whereas in all these other reactors, you have solid fuel rods that are being bombarded with neutrons. But all of these reactors, they use up to 5% nuclear fuel or can. They depend on either water or heavy water as the coolant and sometimes the moderator. And they're at high pressure because, these power plants are typically running at 300 degrees Celsius. So you have to keep the water under something like 150 atmospheres of pressure to keep it in a liquid form. But all of them except the CANDU have to be shut down every 18 to 24 months to refuel. The CANDU can actually be refueled while it's online, so that's a nice feature of that. So here's a picture showing some fuel rods. They're typically uranium oxide pellets that are put into rods that are basically covered with a zircaloy alloy, which stands up fairly well to all the radiation and bombardment that's going on, when the reactor is active. Now, more recently, uh, there's another type of fuel that's been developed called TRISO. Tri-structural isotropic is what that stands for. And basically, it's a small poppy-sized seed pellet, uh, very, very small, but it's coated in layers of carbon and ceramics, which makes it basically impossible to melt down. But it's just, even though it's such a small size, one of those poppy-sized seed kernels containing uranium has enough energy to equate to like 4 tons of coal. And some of this triso fuel is what's going to be used in some of the upcoming advanced reactors, which I'll describe to you in a bit. Now, I mentioned moderators. So neutrons, when you produce the neutrons, when they're coming out of the uranium atoms, they're moving really fast. And most of the time, you want to slow them down because if you don't slow them down, too many of them escape the reactor and the chain reaction dies. So you have a moderator. That can be water, and it typically is in most reactors today. Might be heavy water in the case of the CANDU, or it can even be something like graphite surrounding the reactor. And some of the earliest reactors use that. Actually, some of the Russian RBMK reactors use that. And actually, I think some of the newer designs are going to use graphite. So most of the time, you're trying to get your neutrons slowed down to where you see the thermal neutron equilibrium. The cross section, which is the up arrow, is basically, you could think of this as a target, and the target's getting bigger where the blue line goes up. So that means in that range, you've got a better chance of your neutron hitting another uranium atom and keeping the chain reaction going. Um, Now, there is something called a fast reactor, which uses the fast neutrons that you see there, and I probably don't need to get into that much in detail. The US experimented with those more in the 70s, and I think that really didn't go as well as they would have liked, and so they kind of, just abandoned doing that. But for the most part, but there is some revitalization of that type of reactor as well in some of the new advanced reactors. But for the most part, especially if we're talking thorium reactors, we're going with those slow neutrons, the thermal spectrum neutrons. Now, you also have to have a coolant because when you've got the chain reaction going on, you're producing a great deal of heat, and you've got to remove that heat from the reactor. Uh, in today's reactors, you need to do that not only because that's the heat is producing your energy, but that you want to turn into electricity, but you also want to make sure the core maintains an appropriate temperature so it doesn't get too hot. Now, in some of the modern reactors that I'll talk about later, that may not be as much of a problem. But coolants that are primarily used today are water and heavy water. There are reactors that use helium gas as a coolant. Um, those were especially used in Great Britain some years ago. A few of those are probably still in use, although a lot of them have been shut down. There are also reactors that can use liquid metal as a coolant. And the coolant, it affects the reactor's efficiency. And, one of the limitations of using water, which is what we use today, is that you have the potential for a steam explosion. There's no danger of a nuclear power plant is not going to explode because for it to do that in a nuclear sense, because for it to do that, it would have to have uranium that is at a much, much higher concentration than what's used in a reactor. But what it can do is have a steam explosion because you're using water. So that's the reason that power plants typically have very thick concrete reinforced walls, and the plant building is actually much larger than the reactor itself. And that's to accommodate that steam because steam expands so much versus the water when it turns into steam. Now, typically, liquid metal reactors use something like liquid sodium, liquid lead, or bismuth as the coolant. And today's commercial reactors have several advantages and disadvantages. Uh, as I've already mentioned, they're a highly concentrated energy source. They really have a good overall safety record. Some of the disadvantages are the expense and the slow construction of large power plants. And that's one of the reasons today that we're trying to move more towards smaller plants. But the reason I have an asterisk there is because um, really a lot of that expense has to do with legal issues. If we can reduce the legal issues, we could actually save a lot of money in building these power plants. I'll take India, for example. They build nuclear power plants well today. They're building quite a few, and they are doing it for probably a third of the cost that they're being built in the US. And they're doing it safely, so it's some of these legal issues have to be dealt with. Um, the containment building that I just mentioned, that's typically like a 2 meter thick reinforced concrete, very large building. So that's expensive to build. And that's, as I said, to contain the steam explosion. So if you can if you could somehow get rid of that issue, then you wouldn't necessarily have to have such an expensive containment building. Um, their extraction is limited because, you put fuel rods in the reactor and Even though they create so much energy, uh, the zircaloy alloy that surrounds the uranium oxide just it can't handle being in the reactor longer than a few years. So that's why you have to take it out and replace it with new fuel rods. Well, unfortunately, you've only burned up about 5% of the fuel that's in the rod at that point. So you're really wasting a lot of the uranium oxide that's in there. Also, we have to ask, okay, how much U-235 is in the world, which is what we're burning right now. It's kind of like burning platinum in a way. As I said already, only 0.7% of the uranium that you mine is U-235. There's still plenty of it available now, but is that going to be true in 100 years? I'm not sure. And then you have the decay products because you're not burning up, you're only burning up 5% of the fuel, but it's before you have to remove it. Uh, you have a lot of fission products or decay products that you're not using, and that what we typically call radioactive waste, but it's probably a better term is spent fuel. And that leads me to talking about spent fuel. There is a lot of good, useful fuel in waste, what we call waste. So it's really not waste. The problem is it's it hasn't been economically viable up to this point to reprocess that fuel and use it again. And that's one of the issues that we're also working on is reusing it because if we could reuse it or if we could burn it up uh, a lot more effectively, then we wouldn't have so much waste to worry about. Now, I want to spend a little time on this chart because this is very important, and I think it ties into uh, being biblically faithful with the resources that God has given us. Um, there's something called energy return on investment, and this is where the debate comes in with renewables and fossil fuels and other fuels because not all fuels are created equal. Um, Unfortunately, ethanol, which we all have about maybe up to 10% of in our gasoline, maybe 15% in some cases, um, it's not, you're not really getting anything out. You're not really gaining or losing with ethanol for the most part. It's costing about as much to make it in energy as the energy you get out of it, basically. It does vary a little bit with the type of plant you're using. So, like for instance, uh, if you use something like a sugar cane instead of a corn uh, plant, you're going to get a better result. But overall, it's just not. You're not really gaining or losing much using ethanol. Because its energy return on investment basically doesn't even quite reach what we call an economic threshold, where you're actually getting more energy than you're putting into it. That's what we really want. Um, with solar, it really depends on where you are. Um, and what buffered and unbuffered means is, with solar and wind, they're not you don't have the wind blowing all the time. You don't have the sun shining all the time. So if you use it, you have to store it. You have to have like battery storage or something or thermal storage. And you also have to be able to transport it over some type of power lines to somewhere it's needed. It may be where you're collecting it is not where it's needed. And so that's what buffered means basically. So when you factor that in, then in places like Germany, wind and solar, even though they're using wind a lot, you're really probably spending more energy than you're getting out of it most of the time. Not all the time, but most of the time. But however, if you're in the Sahara Desert, you might do very well, for example, with solar, especially concentrated solar power. So for solar, it depends on your latitude, you know. Obviously, if you're at a high latitude, you're probably not going to do well with it. Um, I realize that you have more sunshine in the summer and say somewhere like Alaska, but you're going to have to, your solar is still going to be pretty weak. It's not going to be very intense sunlight. Um, Then you move on up to coal technologies, and you can see that you definitely get, somewhere like 28 to 30 times the energy out that you expended getting it. Hydro is even better, um, but there's only so much hydro to go around. There's only so many places we can install it. But you can see that nuclear by far is the best. It's about 75 times the amount of energy out versus the energy in. And I believe that if advanced reactors are done right, it could even be a better ratio than that. But I think the thing to remember here is that nuclear fuels contain 1 million times more heat per unit mass than fossil fuels. So if we can solve the problems of uh, legal problems and the extensiveness of the building, those kinds of things, I think we can really make nuclear very effective. And this is the nuclear that we have today, which, as I'm pointing out, is not really, I mean, there's lots of ways we can improve on it. And I think that reminds me of the parable of the minas in Luke 19, because, where the servant started out with the same amount, but the one that produced 5 minas from one or 10 minas from one were rewarded for their faithfulness. And I think that applies to what we're talking about here to energy return on investment. Some energy sources are not the same, and it makes sense to go after the ones that uh, produce the best outcome for society. And obviously, we want to factor in how it's affecting the environment there, but at least in the case of nuclear, I think we may be able to do that in a way that benefits us greatly and also benefits the environment. So now I'm going to sort of shift into the link between climate and energy. Um, Obviously, even if you remove the whole climate change discussion from the debate, oil, shale gas, things like that are not going to last forever. We may still have a lot of it around, but eventually we're going to have to think about other energy sources. But there are energy sources out there that haven't even been tapped that would be considered fossil fuels, like methane hydrates, for example, that essentially live in the offshore uh, sh ocean shells, which have barely, really haven't been even tapped yet. But in 2021, production of CO2 was about 36.6 gigatons. That should grow by close to 10% by 2030. But that's a long way from the targets that have been put forward. By 2050. We would have to reduce that to about zero point 0.1 to zero point 0.2 gigatons per year to meet those compliance targets. I can, at least my personal opinion, I can tell you that's just not going to happen. Um, in 23, global fuel costs reached 13% of global GDP. And since global GDP in 22 was about $100 trillion, that was about $13 trillion. The global economy uh, is estimated to require 637 quads of energy by 2030. One quad is about 293,000 megawatts. And that's a 58 quad increase from 2023 to 2030, which equates out to 1,940 1 gigawatt power sources. So if you think of a 1 gigawatt nuclear power plant, 1,940 of those. So the energy demand globally is huge. Um, as of 24, the global economy consumes about 103 million barrels of oil per day. And that's expected to increase by roughly 9% by 2030. So that leads us to a question about climate. There's a lot of focus on carbon dioxide when you have this discussion. And again, this is an area that I could spend 3 hours talking about by itself. And so I only really have a brief few slides in here. But there's actually a lot more than carbon dioxide to consider when we talk about radiative feedbacks. In other words, essentially increasing the balance or imbalance of the solar radiation that we get and the heat that remains in the atmosphere or is captured temporarily at least by the greenhouse effect, as we call it. There's tropospheric ozone. Uh, Ozone's great in the stratosphere. It's not so great at the surface. It's produced indirectly by other pollutants, zero point 0.4 watts. So the total imbalance is like considered to be 2.7 watts per meter squared. Methane is another 0.55 watts. Nitrous oxides adds a little bit more. Aerosol black carbon. So that's like black carbon from fossil fuels. Let's say it gets deposited on light surfaces, especially things like snow and ice. It can have a positive feedback. And then snow and ice is listed there too, in addition to that. Then now the aerosol black carbon, I meant to say, is also up in the atmosphere. So that has an effect on its own, besides laying on snow and ice. But the really uncertain ones are aerosols in general. Uh, Many of the aerosols are believed to have had a negative impact on the radiative imbalance. And also we have shortwave radiation effects, clouds, albedo. And by shortwave, I mean the sunlight that's essentially coming in. The incoming sunlight is shortwave, the outgoing is long wave, a little bit longer wavelengths. But because of the uncertainties related to cloud albedo and aerosols, uh, that's why there's such a wide range there on the carbon dioxide, zero point 0.8 to 2. Um, there are other factors like changes in glaciers, changes in solar radiation, and I don't have time to go into this, but we recently discovered a lot of impacts that occur on the effects of solar radiation as it relates to the stratosphere and things that go on in the stratosphere. Also, we have urban landscapes. Now, urban landscapes, they're not greenhouse gases, but they're still human effects. Um, you change the surface to asphalt and concrete in a large enough area, it has an impact on how much solar radiation is absorbed and then re-emitted and how it's re-emitted. And these effects can be as much as 1C all the way up to 12C if it's a mega city. And it depends on the background weather as well. So in certain circumstances, certain weather conditions, the effect will be very small, and then other times it'll be very large. And it's also, of course, a lot more localized than, the world at large. Now, having said all that, I really think that it might be time to stop focusing so much on CO2 because so what this diagram is basically showing you, in order to make this work, I had to turn it on its side, but basically on the left is the surface, and then the yellow is the air pressure in millibars as you're going up through this troposphere and stratosphere. So going to the right is toward the top of the atmosphere. And what this is showing you is the amount of radiative impact in the atmosphere at various levels for carbon dioxide um, in the tropics. And so blue bars are 0 to 280 parts per million. So if we had zero carbon dioxide and we went up to 280, which is basically what it was in 1850 or thereabouts, you can see there's a significant impact in the troposphere and warming the troposphere from CO2. There's actually a cooling effect in much of the stratosphere. But you also notice that if we now go from 280 to 560 parts per million, there is still a warming effect in much of the troposphere, but it's not that much. And so, and we're about halfway between that 280 and 560 right now at about 420. So I think what this is suggesting is that most of the warming to the atmosphere that's from CO2 has already happened. Probably about 90% of it has already happened. And additional warming that we get is, it's probably going to be from, if we get it, it's going to be from a lot of these other things, but not so much from CO2. And if you go up to the subpolar regions, you kind of see similar effects, although you see much more cooling in the stratosphere. That's why the actually on the Antarctic plateau, the ice sheet, the effect of CO2 is actually more of cooling than it is of warming because of the really high elevation there. So that leads me to talk about climate sensitivity for a moment. And climate sensitivity, that's essentially uh, talking about if you double CO2 or add various greenhouse gases, how much is it going to warm? How much is it going to warm the atmosphere? And there are various ways that scientists have addressed this question. And let me see if I can find it. There it is. So climate sensitivity is defined as the global surface warming that occurs when the concentration of CO2 in the atmosphere is doubled relative to pre-industrial levels. It's highly debated, and it should not be thought of as being an entirely constant value. So the chart you're seeing there, uh, on the right, the orange section, these are estimates of climate sensitivity based on basically climate models. So you can see the average there in the orange line is roughly 3C, and the max and mins are, pretty wide ranges down to as low as 1C and as high as almost 6C. But then over on the left in the blue section, those are climate sensitivities that have been based more on historical observations or paleoclimate research. Like we've looked at, what was going on at the last glacial maximum and how much warming and cooling occurred. And you can see there that most of the climate sensitivity average is pretty close to 2C rather than 3C. And the extremes are not quite as great either. So that would suggest, going by that data, that it's somewhere between 2 and 2.5C for the climate sensitivity. Hang on a second here. Now, I think I need to mention too about the concept of adaptation and mitigation and thrivability. Thrivability is the ability of the basically our society to be able to prosper. And this leads into the discussion about mitigation and adaptation. When we're talking about mitigation, this is like we're trying to reduce carbon emissions because we think that will uh, prevent some measure or amount of climate change. Um, Adaptation is really more uh, taking measures to uh, protect against changes that are occurring. And that's an important question because we really have to answer the question is what makes the most sense, uh, not only for the environment, but for economically. I mean, if we can't even have an economy, if we do a certain thing, that's a problem. Um, and this chart is basically showing you weather and climate related deaths since the 1920s. And you can see that they have decreased by decade on average about 95% in roughly 100 years. And that's because of fossil fuels, because people are able, when people have energy available to them, they are able to protect themselves better and build infrastructure and do things to protect themselves from the environment. And that's basically what's happened here. So that's a really great illustration of adaptation. And the reason I'm really questioning, I'm not saying we shouldn't mitigate if we can, but the reason I'm really questioning that we should be focusing so much on mitigation is this chart right here. Now, I didn't really have time to explain to you what the RCPs there on the chart, but basically, when climate models are run, they have all these possible scenarios, possible outcomes. And RCP 8.5 is like the worst. They all have assumptions built into them, like how much energy, how much coal is used, all kinds of different things, how much the economy grows, the population, so on. And for many years, RCP 8.5 was considered the business as usual scenario, but it's become apparent in the last, say, 5 to 10 years that RCP 8.5 is really not realistic. It's just there's not any way we can make it happen. RCP 4.5 is probably closer to realistic as far as business as usual, and the numbers correlate to the imbalance of watts per meter squared in the global climate. Again, I could spend a lot of time talking about that. But what this chart is basically showing is that the warming that we have been seeing, and it looks like we will be seeing based on historical and paleoclimate data, is falling in that blue-gray zone right there between about 2.1 and 2.8 C. And the orange graph is showing you the cost of climate policy implementation, and then the blue line is showing you the cost to the economy from the climate change itself. So you see there that until we get above RCP 4.5, the cost of climate policy is actually way more expensive than the cost from climate change. So unless we can see that we're going to be above RCP 4.5, it really probably makes more sense to focus more on adaptation. So I think, yes, I think, and I say this to say that while I think nuclear energy does have great potential for mitigation because it is a fossil-free fuel source, I think we need to look at it in a more practical sense as well, just because it makes more sense. It has a much higher energy density, and eventually we're going to run out of fossil fuels and we're going to need it anyway. Um, but I'm not really personally that, well, I do think we have definitely seen warming and we are seeing warming. I'm not saying there's no such thing as warming. I'm not saying that at all, but I am saying, um, we've got to look at these numbers realistically, and these seem to be the realistic numbers. I've been in this business for 35 to 40 years now. So let's get back to the nuclear. How can new nuclear and thorium help us care for the climate better and encourage human thriving? And for that, I have to go back just for a moment to the 1960s. And this is Alvin Weinberg. Alvin Weinberg was the director of Oakridge National Lab from 1955 to 1972. Very smart guy. And he actually was responsible in a large part for the molten salt reactor experiment that happened in Oakridge. It actually started with the Air Force wanting nuclear-powered airplanes, believe it or not. And he knew that wasn't going to pan out, but he saw the potential in molten salt reactors nonetheless. And that led to the molten salt reactor experiment. But basically, this is what he said about it. The project was basically canned in the early 70s. And unfortunately, the US government chose to go a different direction, even though he told them that this was a good way to go. And then this guy was, at the time, Mr. Nuclear Energy. But he says the molten salt technology is entirely different from the technology of any other reactor. To the inexperienced, fluoride technology is daunting. Perhaps the moral to be drawn is that a technology that differs too much from an existing technology, and he's talking about the type of reactors I've already described to you, has not one hurdle but to overcome, but to demonstrate its feasibility, but an even greater one to convince influential individuals and organizations who are intellectually and emotionally attached to a different technology that they should adopt a new path. It was a successful technology that was dropped because it was too different from the main lines of reactor development. I hope that in a second nuclear era, the fluoride reactor technology will be resurrected. Well, we are now entering that second era, so hopefully his objective there will be met. And so this is a picture of the molten salt reactor experiment, the inside of the reactor. Um, I think the important, I could spend again a lot of time explaining the parts to that, but I think the important thing is that it had it had a feature which first of all, it doesn't have water involved, so you don't have any danger of a steam explosion. And if it were to shut down, you really can just walk away from it because the molten salt, which contains the uranium fuel in it, just flows down into drain tanks, and then nothing, the reaction shuts down because of that. So unlike reactors that we've had in the past, you don't have to worry about a meltdown or something like that. Um, I'll get a little more to that in a moment. Now, there really hasn't been a molten salt reactor in operation since this one, uh, since about 1970 until 2022. Um, this guy is still sitting there, not doing anything, very close to where I work. But in 2022, China set up an experimental molten salt reactor that was largely patterned after the one in Oak Ridge that was built in the 60s. And it's a 2 megawatt reactor, not a very big reactor, but it is running. And their goal is to create uh, larger versions of this that will actually produce power by 2030. I believe it's somewhere in the northwest part of China in the desert. Now they haven't, I don't believe well, actually, I think they are using some thorium in it. So now there are actually multiple types of molten salt, but one of the very promising ones is called FLIBE. And that is an acronym created from uh, fluoride, lithium, and beryllium. So it's lithium 2, beryllium, fluoride 4. Um, and basically, your uranium fuel gets dissolved in this molten salt. Now, the great thing about the molten salt here is look at its liquid temperature range, 459 C to 1430 C. Um, and I see I'm running a little behind here, so I'm trying to speed it up a little, but that's almost 1,000 degree temperature range that you can operate your reactor in, and you don't have to worry about it freezing or boiling. When we're running water reactors today, we're we have a much tighter temperature range than that. Also, FLIBE has 8.5 times the heat capacity of water. Um, so it's both a nuclear solvent and a coolant, and it has high chemical stability in a high neutron gamma radiation environment, which is what you have in a reactor. Um, and so now I'm going to show you real quick a couple of several reactors that are being developed. So the Kairos reactor is probably one of the ones that's going to come online the quickest, and this is actually being built in Oak Ridge. This one is a 15 megawatt demonstration reactor, likely to be online in 27, being built as we speak. And it's basically a prototype of a 140 watt operational power plant, which they hope to have operational by the early 2030s. A couple of things I want you to notice about it. Now, it is not using thorium yet, but it is using the triso fuel. And it is using the molten salt. So this is kind of like a step toward the thorium reactor. So there's no possibility of meltdown, no possibility of a steam explosion. It operate, water reactors operate at 150 atmospheres of pressure, a lot of pressure. Um, this one operates at atmospheric pressure. So you're not going to have an explosion of that nature. Reactors today have 33% efficiency. In other words, two-thirds of the heat energy goes out the goes out the stack. This one has an efficiency of 45%, so that's about a 50% increase in efficiency. The refueling is online. You don't have to shut it down. If something happens, it just shuts itself down. You don't have to do anything special. Um, Hopefully, this will be powering parts of the US by the 2030s. Um, This is just a diagram of it. The pebbles go in the sides, they come up from the bottom, they circulate. Another great thing about this is because the pebbles are circulating, they can stay in the reactor a lot longer than those fuel rods could, and therefore burn up a lot more of the fissionable material and therefore reduce the amount of waste. Another promising reactor is the TerraPower Hitachi GE Natrium reactor. This is being built in Wyoming. Um, This one actually uses liquid fuel. I'm sorry, liquid sodium for the coolant. And it's 345 megawatts. It has the ability to go up to 500 megawatts for like 5 to 6 hours, which is very useful because if any of you know anything about the power industry, you know that power demand fluctuates wildly, and it's actually quite an amazing thing that the power industry is able to balance load the way they do. This will help you do that. This also has a pretty high efficiency. It's that should say delayed to 2030 there. Um, and the reason is it uses HALEU fuel, which is high assay, low enriched uranium. That's uranium that's enriched up to 20%. So that is a lot higher than what's been traditionally used, 3 to 5%. But they're essentially waiting on the Department of Energy to get enough of it produced. So they think they'll be able to start this up about 2030. And then at the Idaho National Lab, they have the Elysium molten chloride salt fast reactor. So this is one of those fast reactors that doesn't really use a moderator because it's using the fast neutrons. Um, but the main thing about this one is, and it's using molten chloride salt instead of molten fluoride salt like the FLIBE is. Um, the really great thing about this one is its goal is to use spent fuel. All this nuclear waste or spent fuel that is stored in various places in the U.S. As I said, that has a lot of energy in it, potentially usable energy in it. Um, it can be burned in this reactor, so therefore it can be reused. So this is a diagram of an actual thorium reactor. So the main thing you need to see here is that there's what's called a thorium blanket around the core. So you're actually burning. You start a thorium reactor with U-235 like a normal reactor, but once you get it started, you can produce. You have your thorium around the edge here where the neutrons coming out of the core can hit it. That takes it through that process I showed you earlier where it ends up turning into uranium-233. And so once it's uranium-233, it can be put in the reactor. That takes about 4 weeks. It can be put in the reactor. And so essentially, what you're doing is as you continue to put thorium in this blanket, you're continuously creating uranium-233 to burn in the reactor. So as long as you have a supply of thorium, it's a pretty self-sustaining process. And I need to make the mention that there's 400 times as much thorium in the world as there is uranium-235. So if we can actually use the thorium in reactors, convert it to U-233, we have a huge fuel source here. Um, and it eliminates a lot of the nuclear waste problem because because the fuel is dissolved in the molten salt in liquid form. Uh, you you don't have to take fuel rods out. You can leave it in the reactor until 95 to 99% of the fuel is burned up. That means you end up with 1 to 5% of the nuclear waste of a current reactor, typical reactor. So this means that, so for example, a typical light water reactor, PWR, that we have today might use 38,000 tons of mined uranium over 200 years. But a thorium molten salt reactor started with U-235 and using thorium would only use 600 tons of uranium-235 over that same period. So you're really making the best use of your uranium that's available. Um, Also, the nuclear waste from a light water reactor like we have today may have to be stored for 10,000 to a million years, but the nuclear waste, which is much less to start with, that comes out of a thermal molten salt reactor, 83% of it has decayed enough in 10 years that you can use the isotopes for industry and medicine. For example, actinium-225 is one of the things that comes out of this. And actinium-225 is like a miracle treatment for cancer. I mean, my dad has been battling prostate cancer for 24 years. It's a miracle he's still alive. But if he could have been treated with actinium, I'm sure it would have cleared up a long time ago. The problem is actinium is made today. In fact, Oakridge is one of the places that makes it, but it's a very small quantity, and so it's only enough to like treat maybe 200 or 300 people in the world. But if we had molten salt reactors running on thorium, we'd have probably all the actinium we would need. And then the remaining waste that's left only requires storage for up to about 300 years as opposed to 10,000 or more. So just to get to the sort of the end of it here, um, there are a lot of advantages of using a molten salt reactor and especially a thorium molten salt reactor. I've already mentioned several. You don't have to worry about high pressure coolant and steam explosions. Uh, Unlike plutonium, you can use that low absorption cross section. So in other words, you got the bigger target for the uranium-233 to hit that's produced by the thorium. Um, because it's operating at a much higher temperature than a current day reactor. So we're talking 600 degrees C or more as opposed to 300 C. And the hotter the temperature you're running it at, the more thermally efficient it is and the more energy you can get out of it. You greatly reduce the fission waste products. I haven't mentioned it, but xenon 135 is a gaseous byproduct of nuclear reactions. And if you get too much of that built up in your reactor, it can be a problem. That was one of the things that caused the problem at Chernobyl. And the nice thing about molten salt reactor is that xenon 135, because it's gas, just kind of is very easy to remove from the molten salt, which is liquid. Uh, you have a liquid spent fuel waste. I just mentioned how much more abundant thorium is, medical isotopes. Also, it produces plutonium-238. That's different than 239. That is used to propel unmanned spacecraft, and NASA is getting very low on plutonium-238. It also helps in rare earth mineral production because when rare earth minerals are produced today, one of the things they find with a lot of these rare earths is thorium. And they just kind of set it to the side because they don't have anything to do with it. Well, if we start building reactors that use it, then we'll have something to do with it. Um, and of course, it's fossil fuel free. And then there are some challenges, and we are working on those. If you operate much above 700 C, theoretically with the molten salt, you could go up to like 1400 C, increase efficiency more. You start having problems with surface corrosion. Um, We also need lithium 7, which, we've got to build supply chains for lithium. Fusion power also needs lithium 6. Um, Kairos Power uh, and China are both developing supply chains. These are also needed to minimize tritium production. Tritium, is a radioactive isotope of hydrogen that is produced in greater amounts in a molten salt reactor. Also, with FLIBE, you've got beryllium toxicity. There are some alternative molten salts that don't include beryllium that are being tested. Um, there's more research needed on FLIBE's heat transfer properties and also on its purity properties. Um, when FLIBE is at room temperature, it produces fluorine, so you need to deal with that. And then you got to figure out where to remove the tritium. Should you remove it in the heat exchangers, secondary loop? And there's some issues with the structural alloys that appear to need chrome, but you can manage that if it's below 700 C. Now, um, one thing I'll just mention in brief here, most reactors and in fact general power plants in general today use steam generators to produce steam that then goes into the turbine. Um, One way of possibly dealing with the tritium removal and making the energy production even more efficient is to go away from a steam turbine and use supercritical CO2. So that's CO2 that's at basically it has the properties of both a liquid and a gas, and it can be used to drive a much smaller turbine. Um, the nice now, I said just earlier how it was great that we didn't have to do anything under pressure, with the molten salt reactor, and you are doing it under pressure with this CO2, but it's not really a problem because of its size. That guy's standing there next to a turbine, and look how huge that thing is. Now, a supercritical CO2 turbine, he could hold it in his hands or in his arms. It's, like maybe 6 feet wide or something. And it is also, as you can see from this chart up here, creates much better efficiencies than helium and can go to much higher temperatures than steam can. So people are working on that as well. Um, the last 2 years, I went to a molten salt reactor conference. So fortunately, unfortunately, this all sort of died out in the 70s, after our lab director was unsuccessful in promoting it. Um, but a revival has happened, since about 2008 to 2010. And for the last 10 years, there's been a molten salt reactor conference here in Knoxville and Oakridge. And I went the last 2 years, and there are something like 400 people coming to that conference now. Um, and a lot of our different national labs are working on a lot of aspects of these challenges I was talking about. None of the challenges I would say are deal breakers. They're all things that can be overcome. We just need a little bit of time to refine them. Uh, and I won't go through that long list there, but you can see all these different labs, Idaho National Lab, Pacific Northwest, Oak Ridge, Sandy are all working on different aspects of molten salt technology. Um, and there are also a lot of private companies that are creating molten salt reactors, and many of them do use thorium. I would say most of them plan on coming online in the 2030s, a few in the late 2020s. Um, and there's a lot of different designs, and a lot of these people came and presented at the conference. Um, Realistically, having said all this, I think we probably need about a good 10 years to get things to the point where we actually have molten salt reactors that are producing, power for customers. But certainly there are going to be a lot of prototypes coming online in the next few years. Um, so I guess my bottom line is obviously physics dictates physical outcomes. Wind and solar, for example, I'm not against them. They're fine to a point, but they're just a very diffuse source of energy, and they're never going to be able to provide the amount of power we need to run the global economy. Um, Nuclear power is orders of magnitude more concentrated than fossil fuels, and even a lot more than that when you compare it to wind and solar. Um, an all renewable powered society, while that might be nice, it's not going to happen without nuclear power. Um, and advanced nuclear energy removes or greatly reduces what's really an already safe form of power. But a lot of the issues we do have, like steam explosions, those go away. Um, so I would just say that advanced nuclear makes a lot of sense. And regardless of the amount of climate change that is happening, both from humans or from natural causes, it just makes sense to go this direction. And I think that's the end of it. And I'm probably a little bit over here, but hopefully we can still have a little time for Q&A.
Yeah, I used to live in Copenhagen, and I remember Copenhagen atomics, and it was out near the airport, as I recall. But I didn't know much about it when I lived there in Copenhagen. It wasn't well publicized, but they are making molten salt reactors, as I recall.
Yes, and I think they hope to have a 1 megawatt test reactor online either next year or the year after, is the
Hmm.
info I got from them. So,
Yeah, and Copenhagen itself had a goal of this year being carbon neutral, but I don't think they're going to quite make it.
That's going to change the world if Denmark is carbon neutral. Copenhagen.
well,
Yes.
somebody, I think Marty had a question about the economics of MSRs compared to fusion economics. Um, Fusion is right now, MSRs are the way to go. While I think it's great that we're doing the research on fusion, it's really not as close. With the MSRs, uh, we know the basics of it works. We have some details to work out to make it, a reliable power plant system. But it's nothing that's what I would call a major roadblock. Um, with fusion, we're still not really to the point where we're getting more power out than we put in. And very, I'm cautiously optimistic that there will be something come out of that eventually, but um, it's definitely not within the 10-year time window, anywhere close to that. So right now, I would say MSRs is a much more economical way to go.
I'll just follow on with that, Kevin. My understanding is that the spark reactor at MIT is going to come online, and they expect it to do better than break even somewhere in the next couple of years. Now, that is a prototype,
Yes.
but I think the fusion community is also thinking of having products, scalable and don't know what the right term for it is, but megawatt or gigawatt or whatever the right term, whatever the right level in 10 years. I think um, so. They're targeting 10 years from now also. So that's why I asked about. I don't know the actual economics of either one, so I just I wonder maybe both.
I think they have included a few fusion energy speakers in the MSR conference, and I've heard a few of them, and so I'm kind of basing it on what I've heard there. But yeah, there's a lot. I would say that while it's definitely something that we need to keep working on, I think there's more to overcome there than there is with the MSR. The cost of the MSR should be at least as cheap as existing nuclear, and really, I think it should be cheaper because, for example, because you don't have to worry about steam explosions, then you don't have to have a big, expensive containment building. In fact, a lot of the designs that are being developed they're actually building them like in the ground, like say like in a basement or something, kind of situation where it's most of it's not even above ground, and they can do that because it's smaller. That's harder to do with a 1 gigawatt PWR because it's so big. But a molten salt reactor tends to be a lot smaller, and so it's easier to shield it like by building it into the ground or something, and that's going to save a lot on the construction cost.
There's a question from Mark Morris. Mark, I don't see you online. Uh, his question, I think, is pretty simple. What reactors are used in our submarines?
I'm not too familiar with them, but I'm about 100% sure they are not molten salt reactors. They're
Okay, well,
much
I
smaller.
am, as a retired Navy guy, I am familiar with them, and they're pressurized water reactors,
Yeah,
100%,
yeah,
using uranium.
yeah. But aren't they sort of self-contained so that they don't have to like refuel them like maybe about once every several decades or something? Okay. Well, I think I had heard that some newer designs they were trying to do that. And
That
I
very well may
know
be.
I
Very well.
know well that's where the HALEU comes in I was talking about that might be enriched up to 20%
Hmm.
because with something like that you have the possibility of having a self-contained unit that you don't have to mess with for a long, long time, like maybe 20 or 30 years. Well, I'm not totally up on that either, but I've sort of heard hints of that.
Hmm. Okay. All right. I like Tim Boyle's question. Tim, why don't you unmute yourself and ask your question?
I guess I'm unmuted. Yeah. Just was curious about, realistically, if things go well with the development of these things, how many years would it take to really make a big impact on the energy supply? Is it something that's doable in a relatively short time, or is this going to take 20, 30 years just to scale it up?
I would think it's likely to take 20 or 30 years to scale it up. It even, we've really got to start focusing on these things. I think it would help a lot if we would do something sort of like when the goal was set in the early 60s to put a man on the moon by the end of the decade. I think we need an effort, something like that, uh, with these and similar power sources. People are really working on it. I have been encouraged by the number of people I've met and seen at this conference because 10 years ago there was almost nobody working on it. Um, but it's still
I
going to take some time.
I think the Navy's nuclear reactor program under Admiral Rickover is a great example of how you can do something like that in a pretty short time frame. And I think within 2 or 3 years, Rickover basically got the design approved and started making nuclear submarines. It was like almost a miracle, really, how fast they started making nuclear submarines in the 50s.
In an indirect way, I guess the Navy is responsible for getting us molten salt reactors because essentially the Air Force was jealous of the Navy in the 50s and they wanted nuclear powered stuff. So that's why they came to Ornell and said, "Hey, can you build us a nuclear powered airplane?" And that's kind of how the molten salt reactor got started. So,
Really?
Well, and I think that the decision was really probably in the early 50s. It was really only pressurized water reactors and
yes.
although I think Weinberg definitely had the idea, but uh, Rickover was in too much of a hurry.
Mhm.
Maybe they would have gone to thorium reactors right off the bat, and we would have been a whole lot better, I think. But it
I
didn't.
think if we'd listened to Weinberg in the early 70s, we would have probably had molten salt reactors providing power by the 90s.
I guess what makes me sick is that we had one going for like 5 or 6 years,
Right.
and it's all lost. Well, it's not lost. I mean, the technology is still there, and people know what it is. And oh, and by the way, if we're ready for another question, I have one, and that is you mentioned China, but also I understand India is working on molten salt reactors too.
They are interested in it. I don't think they're as far along as China. However, they can burn the CANDU reactors. You can burn a limited amount of thorium in
Hmm.
them. So I don't know that they've done that yet. I actually so one of the things I've had the opportunity to do at times is build models like computer models of reactors. And one of the ones I built one time was one of those CANDU reactors in India. So I became rather familiar with their nuclear program when I
Hmm.
did that.
I like Ron Breedlove's question. Ron, can you unmute yourself and
Oh, well,
you're muted again.
I guess not.
So that's good. That's good. Now you're okay.
Okay. Given the safety factors of MSRs and all the advantages, is it conceivable that at some point they could replace virtually every other power source?
Yeah.
I suppose it's conceivable, but I mean, when I think realistically, I think that would be a very long time before we reach that point. But you know,
Yeah, I've been a big fan of them for years.
well, once and that's actually what sparked so about 3 years ago, I guess it was, I got much more involved in nuclear reactor safety work. And when I really understood what molten salt reactors were, that's when that's kind of what brought about I don't know if you listened to any of my short talks at RTB last year, but I did a scholar visit last fall, and it was mostly focused on these reactors and things like that. And it because I happened to run into Jeff Zwierink in a conference a few years ago after I'd learned about these things, and I was like, this is the first time I've seen anything in terms of an alternative energy source related to the whole climate issue that might actually make sense, because the wind and solar just wasn't doing it for me. But, this is something that could actually really make a difference.
Thank you.
I my personal feeling is a vehement yes to your question. Could MSRs replace all other power
It's
sources?
just a
I
question of
think,
how long.
yeah, that's true. That's true. But in terms of the amount of thorium that's available and the basic simplicity of the design, I mean, it isn't as simple as you made it sound, but it's
Right.
pretty simple. It's pretty simple in comparison, even with the existing uranium designs. Kirk Birchie, I think, had a question, and he was trying to get his hand raised. So, Kirk, can you hear me?
Yeah. Um, just a second. We're trying to negotiate for a place for there, but uh, but two comments I had. I heard years ago that India was trying to make thorium reactors, and I just wondered how much progress they're making. I guess you kind of answered that with the molten salt reactors. I guess that includes thorium. And the other question I had was, have you heard much talk about accelerator driven subcritical reactors, ADSRs? A decade ago, I was hearing a lot of talk about that at conferences, and I haven't heard much since. And I always thought it sounded like a crazy idea. Um, and so
You
maybe
talking
people have given
about,
up on it.
I may be off base, but are you talking about spallation?
Well, it
Um,
was ADSRs. It was so they built a reactor that was like 98% critical. And to push it over the extra 2%, they would add neutrons from something like a spallation neutron source that you're familiar with there at Oakridge.
yeah.
And so the whole thing just seemed crazy to me. That the selling point was that the reactor was subcritical, so you wouldn't ever have a problem with it melting down. But to build something like a spallation neutron source next to a reactor is just kind of nuts. And then to load the thing so there's 98% critical, I think is just as dangerous as trying to run one that's critical.
Well, I did hear a guy, I did hear a guy give a talk about that, and it is theoretically possible, but it seemed like when he was talking about it, I got two impressions from it. One is it's probably not nearly as close to being something we could use as MSRs are. And the other thing is there were some issues with like starting and stopping it apparently. So I think there's some things they would have to work out related to that. And of course, it's not exactly cheap to build an atom smasher. I mean, the spallation neutron source, several $billion that exists at Oak Ridge. So I think you can build molten salt reactors for far cheaper than that.
I noticed that there was one program that you didn't mention, and I'm not sure what your opinion is, but let's ask it anyway. And I think it's Abilene Christian University has this guy named Rusty Towell that's
Yes.
building a molten salt reactor, and it's going to be underground too. And of course, it's
Yes.
a model reactor. But you want to comment on that one?
Yes, I actually have met him at the MSR conference, and he gave a talk there, and I think I've heard him twice actually. And yeah, it's an exciting thing. Now it's only, it's a 1 megawatt, it's very small, but it's for experimenting and maybe producing some medical isotopes. But it is molten salt reactor, and it will probably be operational maybe as soon as next year. So it probably will be the very first operational molten salt reactor since the MSRE at Oak Ridge
Do you
in
know if
the
there's
US.
is there any commercial interest in that particular one that they might partner with him and turn it into something commercially profitable?
I'm not aware of it specifically, but knowing Rusty, I am sure he is working on it. He is definitely promoting that and really done a lot to make that thing happen. So I'm sure they will not stop with just building it.
And then there's another name that if you've been listening or watching the YouTube channels, you will see this name coming up time after time after time, and that's Kirk Sorensen and
Right.
Flyben.
Right. I haven't heard as much from him lately. I think he did a he did a great service to the community. I would say from about 2010 to 2020, really promoting the technology and bringing it. And I think he generated a lot of good interest, and maybe that's part of the reason there's so many people now working on it.
Hmm.
But I don't know what he's doing now. I haven't seen nearly as many posts from him in the
I,
last few years.
I think that Flybe is still floundering around, and I don't think they have any major funding sources. And he keeps trying to get projects going at the national labs, but nobody's wants to fund him. I don't understand it because he was such a effective promoter for years, as
Yeah.
you said.
I do know he had some type of I would say a moderate to small size DOE project back 3 or 4 years ago, but I don't know what might be happening now.
Mm-hmm. Okay. Hopefully, Flybe won't flub.
Yeah. Well, I mean, definitely some of the new reactors that are coming along are going to use FLIBE. The Kairos reactor is going to use FLIBE molten salt. I mean, Kirk Sorensen's reactor is called the LFTR lifter,
Mm-hmm.
but I don't know that he's gotten a contract to build one anywhere commercially yet.
Yeah. No, I don't think he has, but his company, as I say, is called Flybe Energy, I believe.
Right.
And they, as far as I know, they're still existing, but they must be, I don't think they have much money.
I'd say you're probably right.
Well, okay, Carrie, I love that question. Go for it.
Is the current federal administration is supportive of MSRs?
As best I can tell, yes. I mean, in general, I think they are more supportive of nuclear than some of the other if you want to call it renewable. Uh, so I would be cautiously optimistic, I think.
Yeah,
I
thank you.
don't think I haven't seen anything from this administration that directly supports MSRs, but I think you're right about nuclear. They're more interested in nuclear than the previous administrations.
Well, in the last administration, because I lived through it in terms, at a DOE lab, and I would say they weren't unsupportive of nuclear,
Okay.
but they were a lot more supportive of solar and wind. I mean,
Wind and
most of the
solar,
money was
yes.
going to that.
Yes.
Whereas now there's very little going to solar and wind, but there's probably the same or a little more going to nuclear than was.
And more going to ethanol.
Yeah, like I said, I'm not a fan of ethanol.
Me
It's
too. I was in 1980, but that was for different reasons. I won't go into that. Well, are there any other questions? And here, do all MSRs? Oh, so Karen Jones Budd, go. Why don't you can you unmute yourself and ask your question?
That's a good question.
Why don't we just take it the way it is? Do all MSRs use thorium? If not, does that change the safety profile of different implementations of MSRs? And do any of them breed weapons grade material that people would worry about? These are good questions.
No,
One at a time.
there are many MSRs that do not use thorium. So, like the Kairos Power one does not use thorium. It uses molten salt. Uh, some use uranium. Some are going to use HALEU, which is a little bit more enriched uranium. But in terms of one thing they're not going to do is they're not going to breed plutonium. So that's good as far as the weapons issue. They are going to breed U-233, and in theory, I mean, because that's what you're using for your fuel, but in theory, you can use that. You could use that for a weapon, but the problem is if you start enriching U-233 up to any higher enrichment, you run into some really nasty radioactive decay problems that are bad for humans. And um, so I think that's probably the reason I'm not aware of anybody in the world who's ever tried to do that with U-233. And that's probably why, because you're probably going to end up dead if you do. So, I think it's definitely lowers the risk of that problem.
A kind of a related question I'd like to ask is my understanding is that theoretically anyway, MSRs can be used to use, and you kind of related to it, can be used to burn radioactive waste from uranium plants.
Right.
Wouldn't that take a lot of processing in order to create something that can be dissolved in the in
Not well, apparently, I don't understand all the details, but apparently not. And the way I've had it described to me, um, and it has a lot to do with the fact that you're dissolving it in a liquid.
really high temperature stuff?
Yeah, because in the past, if we wanted to reuse it, we had to chemically separate it and run it through all these processes and then put it back together in solid form. And it's the solid part that makes it a lot harder.
I wonder how, if you were to try to gather together all of the nuclear waste and burn it before you ever uh, created created a thorium-based reactor, I wonder how long you could you could do that. Well, I mean, of course, it depends on what the demand is for. power, I
Well,
guess.
well, the guy behind the molten chloride reactor in INL, that's exactly what he wants to do. He said, I want to burn up all this stuff before I even start using thorium. So
Any other pressing questions? I feel like I'm monopolizing uh, Kevin here. I really love this subject. Oh, okay. So I have one other question, which one of our regulars is Ken Swanson, and Ken asked me the question. Uh, he tends to be very direct in some of his questions, and he wanted to know what's the apologetic value of thorium reactors. And what basically my answer was essentially, well, okay, so if we really have an energy crunch, you know, did God provide the an energy source which is almost limitless in supply at a very low cost and extremely safe? And I mean, to me, that's a kind of an apologetic argument for thorium reactors.
well, yeah, I mean, if we're going to care for the planet and there is no shortage of energy. There's always some form of energy out there to use, but the problem is we have to find a way to be able to efficiently use it. And sometimes it takes, well, almost always it takes a good while to make an adjustment to a new energy source. So, uh, it's typically can't be done overnight.
Well, if there are no further questions, I am going to. Would you be comfortable in closing us with a word of prayer, Kevin, or would you rather I did?
Sure, I can do that.
Good.
Lord, we thank you for this time that we've had, and we pray that we can use this information for your glory and just find ways to promote your gospel to others that need you. And Lord, we just thank you again and pray your blessings in Jesus' name. Amen.